Okay, I've been asked to go over the volume of a box problem. It's from section 2.3 out of module 1. I believe it's number 13. So I'm going to go ahead and show you what the problem looks like here. All right, so this is our situation here. We have a flat piece of cardboard and we want to fold up the corners into a box. So we have to cut a little square out of each corner so that we can then fold up all the 4 flaps to make the sides of the box. All right, so the first thing it's asking is to express the volume of the box as a function of the length x of the side of the square. So basically, based on how much we cut out of that corner, that's going to determine the volume of the box from the pieces that remain. So, and then it's going to, once we have that formula, it asks us to plug in a couple of different numbers and then pick a graph. Is that all it? And then, yeah. So let me go to another screen here. I'm just going to go to my, wait, I have to turn on the camera. Just a second. Take the camera on. All right. And now I'm going to, sorry about that. Let me share the camera. All right. So this is the idea that we have. The particular numbers are going to change for every problem, but the one that I'm looking at, it shows the flat piece of cardboard. It's a little bit wider than it is tall, I guess. So it's 30 inches wide from side to side, 30 inches the other direction. And then we're going to cut this square out of each corner. And depending on how deep we make that cut, of course, you know, the shallower the cut, the bigger the floor of the box. That's this piece here is going to be. But the walls won't be very high. And if we cut it in a little bit further, the walls that we fold up on each side will be taller, but then the middle of the floor will be smaller. So it kind of depends. And each one of those will have a slightly different volume depending on how we make this cut. So the input variable is how deep do we make that cut? Because however far we cut in on this corner, we've got to do the same cuts for all 4 corners. So in general, for any box, the volume of the box is found by taking all 3 dimensions. So you've got the length and the width, and the height, and that will be your cubic units, cubic inches or feet or whatever the linear measurement is. So if we're going to go through this, I'm going to call this part the length, and I'll call this part the width, and I'll call the vertical piece the height. Okay, so if we take this and figure out where these pieces came from this picture, that can help us get started, although I've got the longer side going back this way. So if this represents the longer side, 36 inches from one end to the other, but we've cut that little X length out of this corner, so it's going to be that much shorter, but we also did it to the other corner. So the length would be 36 minus 2 of these mystery cuts. So it would be 36 minus 2 of those corner cuts. That's the length. So that would be this way. So that would be going from here to here would be 36 minus 2x would be going up this side right here. Now going this way, we're starting from a little bit smaller. So it's 30 inches to start and then minus these 2 cuts out of each end. So 30 minus 2x. It doesn't really matter which one we call length and width, but I'm just writing it like this. And then the height is the easy part because how high this is just depending on how deep this cut is. So if I cut out a corner and then I fold this piece up, this little edge right here becomes this edge right here. So that's going to be just however big the cut is. So that would be x. Okay, so this would be the length times width times height, however we wish to write the order of those 3 factors. That will compute the volume of this box, depending on how deep we make that cut. So that's the answer to part A, given that the original piece was a 36 by 30. Now they asked us to plug in specific numbers to kind of see that it doesn't, even though we're starting with the same basic shape to begin with, depending on how big we cut the corners out of it, we're going to get different volumes. So this one, we could just do this on Desmos. So that would be 10, right? 2 times 5. This would be 30 minus, again, the 10, and then times another 5. Well, maybe I can do this a little bit without going to the graphing. So 36 minus 10 is 26. 30 minus 10 would be 20, and then take that times 5. All right, so I'm gonna be smart about this. I'm gonna do these two pieces first. 20 times 5 is 100. 100 times 26 would be 2,600. So that would be 2,600 cubic inches, because the linear measurements were in inches, right here, inches. Then we do the same thing for 11. We'll do 36 minus 2 times 11. And then 30 minus 2 times 11, and then times 11. Well, that's 22. So 36 minus 22, what is that? 14, I hope. 36 minus 22. Yeah, and then we've got 30 minus 22. I can do that one. That's 8, and then times 11. So 14 minus 8. That's 32, 112. So that's 112 times 14. I'm going to break down and get out a calculator at this point. All right, so I've got, what do I have? I've got 100, what did I do? So 14 times 8. I could do 88 times 14. I don't care. Let's just do it. 88 times 14. 1,232. Is that the same as 112 times 11? Yeah, 1,232 cubic inches. So if we look at the volume here, we get quite a lot more volume of the box if we only make a 5-inch cut. If we make an 11-inch cut, we're getting, you know, we can only go in as far as 15 inches because 30 inches, if I take out 15 on both sides, I have nothing left for the floor of the box. So 11 is getting close to the maximum that we could cut out of that, and we just have a little bitty bottom of the box. Okay, so we could have done this. We could have also put this in as a function into Desmos and just plugged in the 5 and the 11 that way. The next one, though, we go back to the question. Let me stop sharing this. I hope I shared that. The screen sharing is paused. We'll see. We go back to the problem and see what it's asking. Once we filled in these first 3 things, now it's asking us to pick a graph. So I'm going to put this into Desmos, but I'm going to notice while I'm looking at this that X goes out to 18 and Y goes up quite a bit higher. Kind of depends on which one's the right one. They all start from 0, 0. So we'll see. It looks like most of them go up to 3,500, so maybe that's what I'll start with. So we've got, I'm hoping that you can see this. I'm just going to type them in the factored form. It was 36 minus 2x. And the next one was 30 minus 2x. Then the last one was just x. So 36 minus 2x times 30 minus 2x minus x. And I'm going to set my window so that x, what was it, goes to 18. And the y is probably going to have to, so I'm going to try that 3,500 that was in most of our choices. Okay, that was a good choice. So if I let it go to 3,500, which I'm looking in most of 3 of the 4 choices, it went from 0 to 3,500, and it has some kind of a peak in there. So comparing the two, see if I can both of them at the same time. Probably not. All right. It ends about halfway on the right side of the window. Let me see when I look about that. 0 to 18. 3,500. So I've got, readjust it again. 0 to 18. Now let's look at it. All right, so it peaks and then it comes down a little more slowly and it kind of hits around 15. Let's go back on. So that's probably this one, part B. So whatever we're gonna select, let's just go on to the next one. The last question now says, what value of X gives the maximum volume for the box? So that means what's the best cut if I want that box to hold as much as possible? So remember the X value is how deep do you make the cut, and the Y value is the volume, and so the higher the Y value, the bigger the volume, so we want this turning point right here. All right, so according to this, if I make a cut of about 5.43 inches out of each corner, I will get the maximum volume at about 20 612. Okay, so we had the graph was part D, and for part E, we're going to look for the peak point there, 5.432, 26112.80. Something like this. I'm being kind of sloppy because I'm just trying to get the points down there. Okay, so the question specifically says, what value of X gives the maximum volume for the box? So let's look over here. So X is the volume of the box, or the cut that you make, 5.43. That would be just how long do you want to make a cut? So that's just in inches. And if it then finally asks for what is the maximum volume possible, I don't think it does ask for that, but that would be the other number, the 2612.82, 881 actually. Okay, that would be the maximum volume, which was very close to what we had when we just plugged in 5. So let me go kind of summarize what we just said there. Okay, so it asked us to choose a graph, and we chose the graph that started up kind of slowly and then and it decreased a little quicker on the other side. So we picked the right graph, and then it asked us how much should we cut, or what should the value of X be to get the maximum volume? Well, the Y values are the volume, and the X value is the inches that you have to cut into the corner. So we find the peak, because that will give us the maximum volume. And it tells us the X value for that is 5.43. So that would be how much we want to cut out of the corner to make the volume of the box be as big as possible. I don't know if the last part, if this was the last question, or if it then goes ahead and says, well, what would the maximum volume be? Same point, but it's the other coordinate. Okay, so probably getting this piece set up is the main thing to get you going. And then it's just like any other function where we're plugging numbers into a function. We're asked to interpret that turning point where it said, how much do we have to cut in order to get the maximum volume, or what is the maximum volume? Both of those numbers answer that type of question. Okay, so I hope that's helpful. Let me go ahead and stop this so I can get it uploaded.